Hey guys, welcome back. Happy Thursday. Um, Today we're going to talk about the Bronsted-Lowry definition of acids and bases. So this is a definition that basically encompasses a bit more than the Arrhenius definition, goes a little bit further than just saying that an acid is something that increases hydronium and a base is something that increases hydroxide. So the Bronsted-Lowry definition, or definitions I should say, because there's one for acid, one for base, it's very simple. In a reaction, anything that gives up a proton, and when we say proton, remember we mean basically a hydrogen atom without the electron, because if you strip an electron away from a hydrogen atom, all you're really left with is a proton. There's no neutron in most hydrogen atoms. So an acid, according to Bronsted-Lowry, is anything that donates a proton. A base is anything that accepts a proton. And so the reason that that is a broader definition, in some ways better, is because if you look at hydrochloric acid, which is of course an Arrhenius acid, because when you add it to water, it creates hydronium, right? So as soon as you see hydronium, you think Arrhenius acid. But it's also a Bronsted-Lowry acid because how does it create that hydronium? Well, it creates it by donating a proton to the water, right? So that makes HCl both an Arrhenius acid because it produces hydronium and a Bronsted-Lowry acid because it donates a proton. Okay. Now, if you look at this reaction, though, here HCl, even though we know it's an acid, would only be an acid according to the Bronsted-Lowry definition because there's no hydronium being created. And the reason for that is the thing that's acting as a base in this reaction, the thing that's accepting a proton, is not water. So therefore there's no hydronium being made. But it is still an acid-base reaction because hydrochloric acid is giving a proton to ammonia, NH3, to turn it into ammonium, which is NH4 plus, and it leaves behind Cl minus. So HCl in this reaction is a Bronsted-Lowry acid, but prior to Bronsted-Lowry, we just had the Arrhenius definition. You know, they would have been like, well, we know it tastes sour, we know it conducts electricity, we know this and this and this about hydrochloric acid, but it doesn't make hydronium when we put it together with ammonia, so is it really an acid? Well, the Bronsted-Lowry definition solves that because it gives a more broader definition. So, okay, so what we call this when a Bronsted-Lowry acid reacts and gives its proton to another substance, we say that this is a proton transfer reaction. So proton transfer just means a Bronsted-Lowry acid, Bronsted-Lowry base, one is giving to the other. And that's exactly what's happening in this reaction. We have hydrofluoric acid, because this would be called hydrogen fluoride if you weren't naming it as an acid. So we have hydrofluoric acid giving its hydrogen to the acetate ion, and that would leave behind fluoride. And it would also give us hydrogen acetate, which you could also call acetic acid. All right, so this is a proton transfer reaction. There's no hydronium, there's no hydroxide in this case. But this is a Bronsted-Lowry acid over here. This is a Bronsted-Lowry base, the acetate. Now this is also where Bronsted-Lowry improves our definition of bases, because previously with Arrhenius we would have just said it's got to make hydroxide. Well, I don't see hydroxide in this equation either, but yet this acetate ion actually is basic, like it acts as a base. So you know, how do we explain that? Well, the Bronsted-Lowry definition does explain it. It says, well, it's not so much that it has to create hydroxide, it's that it accepts a proton. And that's exactly what acetate will do in order to become hydrogen acetate or acetic acid. Now, I want you to notice a couple things that I have drawn here for you. First of all, we know that HF is an acid, so it's got a little A written under it. I just discussed how acetate would be a base, and that's why it has a B under it. This is a two-way reaction. And so that means that once we form the fluoride and the hydrogen acetate or the acetic acid, those two can collide and go back in the other direction. So what I want you to think about is, okay, so what's happening as we go back in the other direction, right? So the reason I have an A written underneath the acetic acid, of course, besides being called acetic acid, we know it's an acid because if we look at the reverse reaction, this acetic acid is losing its H to the F minus, to the fluoride, in order for it to become acetate again, right? And this has a B written next to it because the fluoride is gaining the hydrogen or accepting a hydrogen, which is the Bronsted-Lowry definition of a base. It's accepting the hydrogen from the acetic acid in order for it to become hydrofluoric acid again. Okay, so we have an acid and a base on both sides of a reversible proton transfer reaction. So there's a Bronsted-Lowry acid and base on both sides. We can't have two acids on the same side because if they're on the same side of the equation, that means they have to react with each other. And if I have two proton donors, then there's nobody to accept the protons, right? So you have to have one to give, one to receive on each side of the equation. Now this word conjugate, it says, so the acid, once it's lost its H plus, its proton, is referred to as the conjugate base. So you might be familiar with the word conjugate in Spanish language classes, but in the case of chemistry, conjugate simply means that the two substances are one H apart from one another. Okay, so if I have HF is my acid on the left side of the equation, its conjugate will be found on the right side of the equation, and essentially it's going to be the substance that's just one proton different from it. And the conjugate of an acid will always be a base. So if you look on the left side and you have HF, then on the right side, well, the thing between these two, which is the conjugate of HF? It's the F minus, right? It's just it minus the proton. Okay, so we could do another practice with this, or another example, by saying, all right, without even having a reaction, we could say, what is the conjugate of, let's say, HNO3? So if I had HNO3, nitric acid, if that was my acid, according to the example I've just given you, what would its conjugate base be? Okay, again, without even looking at a full proton transfer reaction, we should know that the conjugate of any acid is just it minus a proton, minus a hydrogen. So the conjugate of HNO3 is NO3 1 minus. In other words, take away the proton. Now, where did we give that proton? Well, we would have to write the full equation in order to know that. Maybe we gave it to water. Maybe this is a simple Arrhenius acid ionization. Maybe we said HNO3 plus H2O gives us hydronium plus nitrate, right? But the point is, you should be able to tell a conjugate simply by adding or subtracting a proton, an H plus. So bases also have conjugates. Like, for example, acetate here is the base on the left side of the equation. So it should have a conjugate acid on the right side of the equation. And you can see I've connected it with arrows already, so you should already know what it is. But since it's a base, it's accepting a proton. So its conjugate will be an acid. In other words, its conjugate will be it with an extra proton. Okay? So it would be the hydrogen acetate or acetic acid. So let's say we're talking about NH3. What would, again, not even putting it with an acid, but let's assume that this is going to act as a base, all right? What would its conjugate acid be? Okay, so its conjugate, if it's a base, its conjugate would just be it after it has accepted a proton, because that's what bases do, right? They accept protons according to Bronsted-Lowry. So if you add a proton, an H plus, don't forget the charge, this is going to be ammonium, NH4 plus. So just it plus a proton, okay? And again, this is not a full equation. This is just saying from this to this. It's a little deceptive, I guess, to draw an arrow. We're not talking about an actual chemical reaction here because I'm just saying, these two are related because they are conjugates of one another. It's not a true reaction like this one is, because I'm not showing the acid and the base. Okay, last thing I want to discuss here is this concept. The conjugate of a strong acid is a weak base. So I want to talk about what that means. Strong acid, weak base. You may have heard these terms before and wondered what they mean. You may have heard before, for example, that H2SO4, battery acid, is a strong acid. It's extremely dangerous. Or HCl, hydrochloric acid, is a strong acid. It's also extremely dangerous. In low enough concentrations, it's not too dangerous. This is actually what's in your stomach to break down the proteins in your food. Um, but still, it's a strong acid. Even at low concentrations, it has that characteristic. So what does that mean? Well, it means that it ionizes 100%. So when we have a reaction like the ionization of HCl with water, and it produces chloride and hydronium, we don't draw the arrow in two ways. And the reason we don't draw the arrow in two ways is because the conjugate of a strong acid, and HCl is on our list of strong acids here, because the conjugate of a strong acid is a weak base. And so hopefully you can recognize the conjugate of hydrochloric acid is just chloride, right? So this is our acid. And I'm not going to write base above Cl minus. I guess I could, but here's the reason why. In order for me to say that chloride is a base, and it is technically the conjugate base of HCl, but in order to be a base, you have to accept a proton, right, according to Bronsted-Lowry. Well, here's the problem with that. HCl is a strong acid. What that means, it is very likely to give up its hydrogen. You can think of it as having a weak attraction with its hydrogen, or the hydrogen is weakly attracted to the covalent bond or to the electrons that it shares with chloride or with chlorine. So it's easily lost, okay? It's so easily lost, and it's so much more stable or low energy after doing so, that once it forms this chloride, which is technically its conjugate base, that chloride will not reaccept a hydrogen. In other words, yes, the right side of this equation is set up to go in the other direction, where the hydronium could act as an acid and give an H to the Cl minus and push the reaction back in this direction to make HCl and H2O again. But because that chloride is so much more stable without the H, then it just doesn't happen. The chloride just stays there in the solution, the hydronium stays there in the solution, and we don't reform really any of the HCl. So that's why the arrow is drawn in one direction, because the conjugate of this strong acid is a weak base, and it's so weak that it really doesn't even act as a base, even though technically it is the conjugate base of the strong acid. An example of a weak acid and how it would behave would be, let's say we were to talk about, let's go with HF, hydrofluoric acid. Okay, so let's just say HF reacts with water. So we're sticking with ionization here. And this is a two-way arrow because once it forms F minus plus hydronium, so this is a weak acid. HF is not only an acid. I'm going to say Wa for weak acid. I could have said Sa for strong acid up there. But because that HF is a weak acid, its conjugate F minus, right, is going to be a relatively strong base. And what does that mean? Well, it means that when that F minus encounters a hydronium, it's going to accept a hydrogen ion from the hydronium. Okay, so that reaction does go in both directions. The other thing that this means is that we can write a KEQ expression for this because it's a reversible reaction. And not sure if we're going to have enough time next week to get into pH and how it relates to KEQ and weak acids, but that is actually a pretty big part of this unit, usually, if we don't run out of time. But anyway, let's go through a couple of questions using this concept of weak and strong acids and conjugates. Okay, so my first question is, even without looking at the list there, because I've drawn a two-way arrow, what does that mean that we can assume about that acetic acid? Okay, so you should have said that it means we can assume that it is a weak acid, right? Because there's a two-way arrow. It's a reversible reaction, okay? So what are my two products going to be for this ionization equation? Okay, so you should have said, and the order doesn't matter, of course, but I'm going to say hydronium and acetate, right? All right. So my next question is, what are the two acids in this equation? Remember, there should be one acid on the left and one acid on the right. Okay, so you should have said that our acids, of course, are acetic acid. That's going to be one of them because it's giving up a proton to the water. And then on the right side, our acid would be the hydronium, which of course by default means the water is acting as a base and so is the acetate in the reverse direction. Okay. And the next thing I want to do is just sort of connect the conjugates. So which substances uh, in this reaction are conjugates of one another? Okay, so you should have said, of course, that the acetic acid and the acetate are conjugates of one another, and the water and the hydronium are conjugates of one another. Okay, the last thing I want to talk about is this little table down here. So this table gives you an idea of which direction will be favored for a reaction. Like, in other words, will a KEQ be bigger or smaller than 1 for these ionization equations, or for any acid-base reaction, really. So all you have to do is compare the two acids in a reaction, or compare the two bases, and it'll tell you, okay? So if I look at this reaction, there's two acids, right? This table gives me a list of relative acid strength. And on the other side, you notice here, the other column is just the conjugate of each of these acids, which of course we would refer to as a base, and it will be um, in reverse order because the strongest acids will have the weakest conjugates. So perchloric acid, which would be the top one up there, has the weakest conjugate base, whereas water, its conjugate would just be hydroxide, and that's going to be the strongest base that you can have. So if I look at this reaction and I want to know which side of the reaction or which side of the equation is favored at equilibrium, all I have to do is compare the acetic acid with the hydronium, and that's going to tell me which one is going to be, which direction is going to be favored, and therefore what will there be more of at equilibrium. So if I compare acetic acid to hydronium, so we're going to find acetic acid on the list, and there we go, HC2H3O2, there it is. So here is acetic acid. There is its conjugate base. And then if I compare that to the other acid-base combination here, it was water and hydronium. So I'm going to find that, so hydronium is acting as an acid, and so here it is. I got to find hydronium on the acid side, water on the base side. Notice water also shows up at the bottom of the list, but that would be water as an acid turning into the conjugate base hydroxide. That's not what's happening in this reaction. Okay, so which one is stronger, hydronium or acetic acid, according to this chart? Right? You would say, oh, hydronium is closer to the top of the list, right? So that means that hydronium is better at donating a proton than acetic acid is. And so if I look at this reaction, the reverse reaction will be favored. And that is because hydronium is better at giving up a hydrogen than acetic acid is. And the same will be true of the bases. Acetate is better at gaining a hydrogen than water is. So the reaction will be favored in the reverse direction, meaning that by the time we reach equilibrium, if the reverse reaction is favored, go ahead and write that down. So for this reaction, the reverse is favored. And so does that mean there's going to be more reactant or more product at equilibrium? So if the reverse reaction is favored, that means we're going to produce more reactants. Oops, I'm in reverse here. Yeah, there we go. More reactants. So that means our KEQ is going to be very small. It's going to be smaller than 1, probably much smaller than 1. So hopefully that makes a little bit of sense. If not, rewatch, email me, show up for our Zoom sessions, and we will see you next week.